Welcome to this tutorial on theoretical insights into training instabilities in deep learning. This is based on the No IPS 2025 tutorial. When training large language model, we ideally want the training loss to go down smoothly over time. However, if you look at this curve, you will see sudden, sharp spikes during training. Why do these loss spikes happen? It turns out that the loss step size we use to train model efficiently are exactly what cause these instabilities. To understand this, let's image the learning rate or step size as a ball rolling down a valley. If we use a very small step size, the training is highly stable. The model takes small, careful steps train down to the bottom. But in the practice, we want to train much faster. If the step size is too large, the process becomes unstable, bouncing wildly back and forth across the valley works. So why do we use these large step size if they cause so much bouncing? Imagine a landscape with both sharp valleys and flat valleys. Large steps actually have the model bounce completely out back sharp areas and eventually settle into wider, faster minima. This is crucial because flat minima have driven the model from overfitting to the data. To control this bouncing, we can use a simple trick called learning rate warm-up. We start with a warm-up phase, steadily increasing the learning rate step by step before lowering it to navigate safely into that flatter region. This warm-up approach prevents early diversions and stabilities the whole training process. Welcome to background of our tutorial on optimization. We will start by reviewing classical optimization theory. Then we'll explore a model take on how large step size actually accelerate training. Finally, we will wrap up with a summary and some open problems. Let's start by reviewing the descent lemma. Classical theory tells us that if the step size is sufficiently small, the loss will decrease smoothly and monotonically. Visually, it looks like taking small, careful steps trend down a valley. But what happens if the step size is too large? The training becomes completely unstable. Instead of sliding down, the algorithm overshoots the bottom and bounces wildly side to side. We can visualize this behavior on a step size spectrum. Down at the bottom is classical theory. Here, we use tiny step size that are stable and act like smooth gradient flow. In the middle is practical deep learning. Here, we use much larger step size that are technically unstable, but still eventually converge. And at the very top, if the step size is infinite or just too large, the model delivers entirely. Interestingly, this middle unstable but conversion zone doesn't even exist for simple quadratic problem. Because of this, we need an alternative mental model. In simple linear regression, unstable conversion is mathematically impossible. The model just bounces outward. However, if we look at logistic regression, this unstable but conversion behavior is both conservable and provable. And moving at the way to modern deep learning, we constantly observe this exact unstable conversion in practice. As you can see in this diagram below, this model experiences sharp spikes in lows before finally settling down. Let's look closely at our phase transition using logistic regression. If we use a small step size, the gray line shows the loss dropping steadily, but very slowly. Now watch the green line representing a large step size. Initially, it's bound around and spike upwards. But look at the happen next. It drops much faster and overtakes the small step size. We just crosses a phase transition. The training moves from a messy, unstable phase into a smooth, unstable phase. So while large steps are initially unstable, they eventually exit that phase and greatly accelerate the overall optimization. What happens to this dynamic if we add L to regulate rotation? Imagine a valley that also acts like a basin. During the unstable phase, the model overshoots, taking massive bounds high across the valley walls. But eventually, it enters the stable phase. The regularization boosts the model back, helping it safely move down to the finite minimizer at the bottom. To summarize what we learned, first, training instabilities is directly caused by using a large step size. However, acceleration is also achieved exactly via this large step size. This gives us a new mental picture of optimization, moving from an unstable phase into a stable phase. Looking ahead, urban problems include finding trackable measures of these trajectories and developing better step size scheduler like warm-up and decays to balance this behavior.